Okay, so this presentation is about settlement in soil or consolidation. My name is Muhsin Hassan, and I hope you enjoy this video. So I'm trying to make it legendary, because soil usually is boring for most people, but I promise it's gonna be legendary. Okay. So we start with the legendary person, Kawasaki, and according to Kawasaki, settlement is defined as the consolidation is any process which involves a decrease in water content of saturated soil without replacement of water by air. So what does that mean? That means that as we compress any material, okay, it will re reduce in volume. That means the voids will decrease in size in a mill, and water will just dissipate or seep out of that void, but it will not be replaced by any air. Okay. Just get later. Yeah, it will not be replaced by any air. So this is the process of consolidation, or in general, it is the process in which reduction in volume takes place by expulsion of water under long-term static loads. And notice it says long-term static loads, and we'll explain what long-term means in a few slides. Okay, so the consequences of consolidation is pretty severe. So if we have a look at this building, we could suffer from something called differential settlement. Differential settlement is basically one side of the building or the structure is going to be sinking in more or deeper than other sides, as you can see here. So this is going to be rotating along one point. Now just imagine you live in this building or you own this building and it becomes that slanted. Obviously you're going to be very upset because this structure now is deemed unsatisfactory and not safe for use. So before building anything, you must run a consolidation test or report to make sure that this soil can carry your building in a safe manner. So how do we do that? We'll see now. So consolidation is broken into three primary parts. We have instantaneous settlement, which happens immediately as we load the soil due to elastic effects, and that is exactly this. So we've got a block or a sponge, and then we load the sponge, and the sponge will expand sideways. Okay, so the initial volume and the final volume are exactly the same. However, it just expanded sideways. Okay, so this is called elastic settlement. Then we have the primary consolidation, and this one is the topic of our video today. And as you can see from this diagram, we can see the instantaneous compression of settlement is very small amount, and the primary consolidation is huge compared to it. Okay, so this is the biggest part. And then we have secondary compression or creep. Okay, could be called creep, and again it's a very small part. So on this axis we have settlement versus time, so it takes long time to get from this point to this point, so it's called long term. So just to put this into perspective, we could imagine that the instantaneous settlement would be like something about 2 mil, the consolidation something about 25 mil, and the creep like half a mil. So in total 27.5 millimeters of total settlement, and the vast majority is the consolidation. Okay, so what exactly is this consolidation? Again, we said it's the seepage of water out of soil. Now soil could be clay or sand. Well, sand is known that it's very permeable, therefore water will seep out of the sand almost instantaneously, leading to only immediate settlement occurring and no consolidation. Okay, while clay soils is highly impermeable and will cling into the water that's inside of it and will never let it go. So water will seep at a very slow rate, and thus we have something called long term. Okay, so the water will seep very slowly, causing long term effects. So how So you can see the settlement happens or increase by time. So what we will do in this video, we only concentrate at the final value, SF, or S infinity, some people call it, because it could happen after 10 or 50 or 100 years actually. And next video I will be talking about ST, which is the value of settlement with time, ST. So S final is a function of the initial height of the clay layer, multiplied by its difference in void ratio between the initial state and the final state of settlement over 1 plus E naught. Okay, so we can get this. This is easy to get, and this is easy to get. However, to find to predict the final void ratio EF, because delta E is EF minus E naught. So we need to get EF, which is the final void ratio. To get this and to get delta E, we need to do something called odometer testing. Okay, we need to do odometer testing. So basically, we put the soil into the chamber like this. We lock it in, and we apply some loads, and the water will seep out. Okay. Then the results that we get, we plot it on this diagram, which is void versus log of effective stress. And I again say log of effective stress. We don't care about total stress. It's only effective stress. So if you look at this from another perspective, let's say we look at the Earth history. Okay, so first soil was covered by oceans for millions of years, and then settlement occurred, and that means the soil at this point, or the stress at this point has increased. So you can see it here. Initially, initial stress, then the stress has increased to 0.2. Okay, then if this process would continue for another million years, let's say, we would be at this point, which is theoretical point, 0.5. So we see a decrease in void ratio with an increase in stress. Then Homo sapiens came and we revolutionized this earth, industrial revolution, and then we are here. So we are UTS building, and then UTS decided, hey, let's build a new building across the road, building 11, let's say. So we need to do a soil investigation so we can avoid having any soil settlement problems with our building. So we dug a pit, took a soil sample. Now, since this sample is taken out of the ground, it's been released from all stresses that was above it. So we would expect some kind of expansion in the soil, and the expansion is modeled as such. Okay, so you can see the stress has decreased. But you might tell me, okay, but we didn't go back to 0.1. Why didn't we go back to 0.1? That's because of plastic strain. Okay, so the particles have arranged themselves in a way that they are irreversible. So plastic strain. So now we are back into this stress value. This is in the lab. So in the lab again, we put this into the machine, odometer testing, and then we would apply some loads until we pass this point, and then we back into our initial track. Okay, and if we would again to release this stress, we would again go back and we have some kind of expansion, and the slope of this line and this line are the same. So we notice something. We notice that the slopes are the same. So we would call this slope or this line the pre-compression curve, and the other line we call it the version curve or the compression curve. In this point at which the stress or the curvature has changed, we call this the compressive stress. Okay, so the compressive stress is defined as the maximum stress the soil has ever taken during its life. Okay, and is defined as the pre-consolidation stress. So in a soil problem, we would be given the slope of the recompression line CR. We would be given the slope of the compression line CC, and the initial stress and the final effective stress. Okay, with all these three effective stress values, we can classify the soil into two categories. If the stress is less than the consolidation stress, the soil will be called over consolidated, okay, as such. So all the zone is over consolidated soil, while if the stress is higher than the consolidated stress, the soil will be called normally consolidated soil. So every soil in this zone, all the stresses in this zone are called normally consolidated. Okay. So the initial stress and the final stress are less than the pre-compression stress. We can find the difference in void ratio using the following technique. So here is our initial stress and its void ratio, final stress and its void ratio. We could say this is the difference in void ratio delta E, which is EF minus E naught, and we could say the slope of this line is CR. Well, the slope of any line is the difference in height over the difference in x, right? So this is the difference in height over the difference in x. And remember, please, this is a log scale. This is log scale. So delta E over delta log sigma. Delta log sigma is sigma final minus log sigma final minus log sigma initial. Now from math, we know that log A minus log B is actually log A over B. So this is how we got this. So now we have delta E is CR log F as sigma F over sigma I. This is for case 1. This is for case 1 when the stresses are below the pre-compressive stress. However, we could have another case where the stresses are above the pre-consolidation stress. Now same concept apply. Now instead of having CR, we have CC. Okay, that's the only difference. So the consolidation properties that we might be able to get out of the test, the odometer testing, are the CC, the CR, and pre-compression pre-compression stress. Now the question is, which one of these indices or values is constant in soil, which one is variable? So we don't want to guess. Basically, CC and CR are constant in soil, while sigma dash BC is variable, and it's a function of sigma dash naught. Okay, so there's a relationship between sigma dash BC and sigma dash naught. So as we go down in soil, the stress is increasing. So we can no longer say at this point this is the maximum stress the soil have seen. As we go down, we have larger stress and larger stress that the soil is seeing. So we can say now that the relationship between sigma BC and sigma dash naught is marginal stress. The difference between sigma dash BC and sigma dash naught is constant. Okay, that is called marginal stress. Okay, or we could say that the ratio of sigma dash BC over sigma initial is also constant, and it's defined as value called OCR. Okay, so OCR is the over consolidation ratio, which is constant. We could avoid this point for now, just don't worry. So that's the concept of settlement. Now in the next videos I'll be explaining some examples on how to apply these concepts, and hopefully you will actually understand the whole thing. And best of luck. Thank you so much.